Hi everyone. We'll give this experiment a little shot here. So it's unfortunate that we missed our review session, and I will record this little live stream to go over some of the basics again in terms of wrapping up the discussion on cycles and preparing for the exam. And one thing for the exam that I didn't mention on Thursday is the importance of making good assumptions and using approximation to your advantage. If you looked at the exams from the past 2 years, if you spend a lot of time on each of the questions, it's difficult to finish in the allotted amount of time. And part of that is intentional, because in order to do good design, you have to be able to think on your feet. And we want to develop not a simple analytical framework for solving all these problems, but rather an intuition for how some of these fundamental concepts work. So part of the exam is also testing your ability to deploy the concepts. As we said Thursday, I specifically mentioned the idea of synthesizing the concepts rather than memorizing the concepts. That's critical, but also being able to make appropriate judgments in terms of approximations, which are very useful in the context of global challenges and aspects of sustainability, because so much of the data requires some sort of approximation and estimation. So to that end, significant digits are not important. And by that I mean most of your answers should not be requiring 3.14159, right? Which I think is a good reference on Pi Day. Happy Pi Day. Pi Day and Snow Day. The use of pi on the exam will be sufficient to use the number 3. So we can say that if a question requires the use of the number pi, 3 is an appropriate number to round to. And if we think about the concept of Jane's carousel, for example, if you needed to know the diameter or area or size for a piece of that design, if you use the number 3 instead of 3.14159, the answer that you get will not substantially change the concept of the design. If you're trying to propose a concept for the rotational momentum, then the number that you get, which is critical for the design of your system, is not going to change the overall concept significantly. That being said, if you did actually build the concept, when you're in the final phase of doing the details, you obviously would need to use more specific numbers. But in the concept of the context of the exam, the strategy should be one of conceptual analysis and demonstration of your ability to leverage the concepts from the class in a productive and intelligent framework. So with that being said, let's go to a little bit review of the final concepts that we didn't get to on Thursday. So we kind of wrapped up quickly discussing the importance of these other biogeochemical cycles. So a biogeochemical cycle is a cycle of an element through the biosphere and how it exchanges between the biosphere, between all the living things that need these elements to grow and flourish. And in the context of the anthropogenic, the human influences on these cycles, the changes we've made to the overall flux of sulfur, nitrogen, and phosphorus are in fact much larger than what we've changed in the flux of carbon. But the carbon cycle is a very, very large cycle. being the main element of organic matter, our change in the flux of carbon is smaller, but that small change has a more explicit impact in its influence on the radiative forcing, right, for climate change. Sulfur, nitrogen, and phosphorus cycles have a more direct influences on land and water systems. So there are some aspects of sulfur and nitrogen cycling in the atmosphere that are also critical. So acid rain is formed in the atmosphere, but the impact of that acid rain that's caused by sulfur being emitted is felt on the water bodies and on the land surfaces. Likewise, nitrogen emissions also have pollution impacts in the atmosphere, but they usually, the direct effects are on the creation of smog in cities, and so the catalytic converters in your cars are trying to get rid of this nitrogen that causes the smog. LA type of smog. So there are two types of smogs. There's the type that's largely particulate matter, and then there is a type that is associated with the production of ozone by the photocatalyzation of nitrogen that's released from automobiles. So the nitrogen cycle has this direct influence sort of at the urban scale, but both nitrogen and phosphorus arguably have a much larger influence on water systems and water ecologies, as we wrapped up last week discussing the way in which it affects the eutrophication of water bodies, the excess nutrients going into water bodies. So with that being said, it's important to understand that in those contexts, these cycles of sulfur, nitrogen, and phosphorus have much more significant changes to their fluxes, right? And a flux is the unit mass exchanged over time, right? So the rate of movement of these chemicals between reservoirs in the biogeochemical cycling, right? So the rate that the nitrogen moves from the atmosphere to the land, to water bodies, to the atmosphere, has been doubled by human activities, which is the same as for sulfur and phosphorus. The flux, again, which in the case of phosphorus, there's a minimal flux into the atmosphere. It's the flux between the biosphere, between ecology and land and water, and the rate in which phosphorus moves in between those bodies, particularly the amount in which is received by our water bodies, has been quadrupled, right? And this again is largely seen in the pollution in water bodies. Okay. Sorry. So runoff is a central theme in all of these, including the acid rain and acid mine drainage. So there's the direct acidification of water bodies through the act of mining coal, because there's acid that gets created in the process of extracting the ore. So water running off and understanding watersheds is again an important concept to relate. And this is again a topological concept, understanding how Princeton sits on the top of a hill and half of our water is flowing down to Lake Carnegie directly, and the other half on the other side of around Nassau Street is flowing down into the Little Brook, the creek that's at the bottom of the hill over on Hamilton Street. So understanding how these cycles move in terms of water bodies, here you see a river, and how land use changes. This is an important aspect for how water bodies interact. So in terms of environmental engineering, the field of environmental engineering was in fact born out of the needs to mitigate the pollution into our water and air bodies. So the sulfur dioxide and nitrogen and nitrates and nitrites that are released into the atmosphere were understood to cause direct pollution, particularly air quality standards. There are these attainment and non-attainment areas that are defined within these standards and help policymakers, well, not policymakers, help communities maintain good air quality standards. And this is something that Marcelo Mena was talking about, the Minister for the Environment in Chile. And one of his main roles is addressing these air quality challenges in the environment. So nitrogen and phosphorus are also then one of the original motivators for the Clean Water Act. So the same way that the Clean Air Act was influenced largely by challenges of smog, nitrogen and phosphorus pollution into water bodies, and the eutrophication, the massive growth of algae, sort of these pictures of our water bodies being dramatically polluted, and the most famous event probably being the fire on the Cuyahoga River. These are all related to how in the 1970s the Clean Water Act was put in place to regulate what industries and organizations and municipalities were allowed to put into their water bodies. So in this case, these are examples of understanding the challenge of these types of solutions. So the result was a direct production of technologies that could address the challenges in terms of the pollution and the changes, again, originating in a fundamental sense from the massive shift in the flux of nitrogen and phosphorus into our water bodies, and the massive shift of the flux of sulfur into our atmosphere. We created regulations that limited systems that would be polluting these reservoirs, and those were things like stack scrubbers to remove sulfur from the smokestacks of power plants, and then wastewater treatment plants, which use advanced technologies to remove the excess nutrients from wastewater streams before the water is put back into a river or a lake. And depending on the water bodies, these regulations can shift. So I don't think it's essential for the exam to know the precise levels of design of these systems, but understanding the capacity of these systems to affect a region, and understanding the way in which terrain, in this case, thinking about, again, the Princeton example, moves acid around sort of the mountain region being different in the context of the way in which acid mine drainage moves around in the mountaintop mining removal processes that go on in West Virginia, and then also in Wyoming. There's challenges to how you mitigate these direct fluxes. And so understanding the flux in a broader context and the change in those systems is sort of the key thing, the key takeaway from all of these different cycles. And the fundamental concepts that relate to that flux, both for sulfur in this case, as well as the other elements, is this concept of residence time. So this is in the reading, and it's one of the terms that you should be familiar with in the context of how the rate of movement of any of these elements in and out of, for example, a water body, are important to understanding the type and developing the types of technologies we need to mitigate these problems. So sulfur, for example, the flux of sulfur into the atmosphere is relatively high in and out of the atmosphere compared to the amount that's in the atmosphere. So if there's a lot moving in and out of the atmosphere, the average time that it stays in the atmosphere is a shorter amount of time, and this time is called the residence time. So the residence time of the element in a reservoir such as the atmosphere, in this case for sulfur, has a short residence time, whereas in the lithosphere, right, in the earth, in the ground, if sulfur is trapped in a rock, the rate that rocks are removed from the lithosphere and released into other reservoirs, the flux of these elements in and out of the lithosphere, in this case for sulfur, is much lower, and so it's on the order of millions of years. So the residence time is much, much longer. And those fluxes that we're changing in the context of the anthropogenic shifts and these rates of sulfur moving into the atmosphere then can be understood because the residence time is shorter. and the sulfur falls out of the atmosphere in faster rates, and that's how acid rain gets created, because the rate of sulfur released into the atmosphere is increased, and then the natural flux of sulfur coming back out of the atmosphere responds to this increased rate, and this acidifies the water in the rain, reducing the pH of the rain, and then causing the pH to be dropped in water bodies. And the interesting thing about sulfur is understanding here in this image, if you think about the weather today, and anytime you look at the Weather Channel, the clouds generally move from left to right across the United States, right, from west to east. So the challenge with sulfur and pollution that is released into the atmosphere and has a short residence time is that if it's released in Ohio, as we discussed, it generally comes down again in New York City. And this is a similar problem for places like Sweden, where a lot of the weather patterns there would cause emissions from the mainland to move up and acidify the climate there. So understanding the second part of the flux outside of the atmosphere and sulfur would be more understanding the biological relationship to the movement of these elements into the biosphere. So in the case of sulfur, it's more a challenge of the acidification of the ecologies impacted by the falling of acid rain. In the case of phosphorus and nitrogen, it's about understanding what happens when we get too many nutrients, right? And so if you allow nutrient runoff to go into water bodies, these elements, which are traditionally growth inhibitors, are no longer inhibiting the growth when they're available in excess. And along with that waste, along with the nutrients, is generally a lot of food. So if you just dump a bunch of carbon into the water that bacteria can grow on, they can't grow to infinity because they don't have enough nitrogen and phosphorus to build all the other parts of their little bodies. So the carbon is the energy component for them to be able to function, and then the nitrogen and phosphorus are the key elements that build the amino acids and allow them to grow and reproduce. So when we take away those two limitations, then we get excess growth. And you can see from a very fundamental level, you can look at the stoichiometry and of biological systems. So right, a grasshopper here has 5 elements of carbon for every 1 element of nitrogen, whereas grass is 33 elements of carbon for 1 element of nitrogen. And again, if you provide 33 units of carbon, which would be fertilizer, in the form of waste food, right, then the grass can grow, as long as you also provide with that some form of nitrogen fertilizer. And so in order to produce enough nitrogen fertilizer for all of our agricultural use, we developed this process called Haber-Bosch process that creates ammonia from atmospheric nitrogen. And that's the process that has enabled a large shift of production of nitrogen fertilizers that, when used in these watersheds, so these are the large Mississippi River Basin watersheds, you can see that particularly from the Missouri River and the upper Mississippi through my homeland of Iowa, right, all these farm fields where nitrogen is used to fertilize the plants, and any excess ends up in these rivers, and then the rivers flow to the Gulf of Mexico, which creates what's labeled here at the bottom as a hypoxic zone. So this is a zone in which the growth limitations have been removed, and so you have a massive growth of algae, and the algae then, when it's not photosynthesizing, it sucks up all the oxygen out of the water, and then any other species higher up the food chain that need oxygen in the water to survive are killed. So we end up with this large dead zone, as it's called. So this is New Orleans. Here you can see it's spitting out all of the sediment, which is sort of food, along with all the residual nitrogen and phosphorus fertilizers that then enable the massive growth of algae that you can see in green, causing the dramatic drop in oxygen levels in the water there and the killing off of any fish in that region, that hypoxic region. And so there's many videos you can watch of how this works. So understanding how eutrophication, which is the excess growth, creates a state of hypoxia, which is the state of lack of oxygen due to the added nutrients, are the two main concepts, the two main takeaways from understanding what happens with nitrogen and phosphorus. And if we go back to the watershed, the other thing to consider is the Great Lakes are also very sensitive to these in a different way slightly than the oceans, but in a similar way. And it's in a different way because the freshwater ecosystem has different needs. So the balance, right, like the grasshopper, the ecosystem in the ocean is slightly different than in lakes, but nevertheless, so the limitations for phosphorus and nitrogen are actually have to be more precisely maintained in places like Chicago, where you have runoff going into Lake Michigan. Although one interesting design point to note is the reversal of the Chicago River was quite the amazing engineering feat, which moved all of the wastewater from Chicago into the Mississippi River Basin and basically pushes all the waste from Chicago now down through the more traditional Mississippi River pollution stream and helps maintain Lake Michigan in a much more pristine state, although there was, as it was quite a polluted water body historically. So we can quantify the amount of excess nitrogen and phosphorus that are produced, and you can see that the great state of Iowa here is one of the largest producers of excess nitrogen because corn is one of the plants that requires the most nitrogen fertilization for growth, and likewise phosphorus as well in terms of excess pollution being produced from the runoff. And you can measure this bit by the way you would study this is you would look at the rates of application, and then you'd also be able to measure the amount that's in the natural water body of the Mississippi River as it flows, and you can account for how much is being added from each of the streams upstream. So in order to mitigate these problems, right, there's a strategy for, in terms of point sources of wastewater production, right, which is the urban component, we've developed methods to treat wastewater. But before we just want to mitigate the end of pipe, we need to think about what's going on upstream and in the production of these fertilizers, and in the application of them. A design solution should first also consider how to fix the problem at its source. So again, nitrogen fertilizers are produced now easily from this Haber process, using a lot of energy, also another source of greenhouse gas emissions from the fuel used to drive this process, converting N2 into ammonia. And then phosphorus, on the other hand, has as I mentioned, an even more interesting challenge in that we mine it and are dramatically changing the rate at which phosphorus is being removed from the lithosphere and being made available globally through all of our ecosystems. And so this can cause a strange shift in the amount of phosphorus in systems available. So places like New Zealand that have very limited amounts of phosphorus can have significant challenges. Whoops. So the farmland is a challenge then in the upstream process of making fertilizers and applying them effectively and trying to avoid any runoff, right? And there are a lot of ways to grow crops in alternative systems, which we'll be learning about after the break. But the main takeaway is understanding that we make these fertilizers and we deploy them, and by deploying them more effectively, we can have major impacts on reducing the pollution. But here in our own space, the pollution that we see in the Raritan Bay here, which is where all of our wastewater and water ends up, well, actually this isn't the Raritan Bay, this is the Long Island Sound. From an urban setting, these are all point sources of pollution where the water is going through wastewater treatment plants. And in terms of the mitigation of this problem, there is an opportunity, and there are a lot of systems we use to address the pollution in our water bodies. For example, here in the Delaware Bay, right, which is another one of our local waterways, the runoff is an issue for the farmland around the bay, but there's also large components from Baltimore, Washington, D.C., and Richmond that are all producing point sources of water. And this is where the regulations are very effective in creating technologies like enhanced biological treatment of wastewater, where we use bacteria to remove the chemicals. So understanding there are technological solutions at the end of pipe in urban systems where we're collecting all the wastewater, all the water that comes from your showers and your toilets goes into large pipes that before they enter the Delaware Bay, or before they enter, in our case, the Millstone River, which runs into the Raritan, is all treated in a way that the water does not contain excess amounts of nitrogen and phosphorus or biological carbon in terms of food for bacteria to grow. So what we do in those processes are remove that excess food. So we remove what's called the biological oxygen demand. So in order to be able to process that Red Bull or the Cliff Bar that you ate to go and play your game of basketball, potentially, go Tigers, win the tournament. The biological oxygen demand is what oxygen you would need to breathe in to process that food that you ate. And so that's what makes the waters hypoxic. When all the algae come out, they eat all the food, and in order to process all of that biological food, all that carbon, they use up all the oxygen in the water. And so what we do, when we're treating water, is we take the stream of dirty wastewater and we blow a bunch of oxygen through it, and we grow a bunch of extra bacteria, and we allow those bacteria to suck up all of that carbon that's sitting in the water, and then the bacteria sits on the bottom of the big trough that we do this in. So we make a big trough, we flow water through it, we put a bunch of oxygen in, and we create this wonderfully termed activated sludge. And activated sludge is just a lot of bacteria that has grown and absorbed all of the carbon out of the water. It's also absorbed a big fraction of the nitrogen and phosphorus, and then we can remove that sludge from the water stream, and then the stream has had the majority of the carbon taken out of it. So we're using sort of the natural process itself to remove the excess nutrients and the excess materials in the water. So we're basically designing a way to enhance the growth and processing of carbon by bacteria. Okay, so I think those are a quick overview of some of the other sulfur, nitrogen, phosphorus issues. I see a couple people have joined. I'll see if there's any other questions on Piazza. I'll stop sharing my screen here. So there's a few people. I don't know if anybody has any questions, you can chat them to me, I think, somehow in here. I haven't used this format before, but I will see if anybody has posted any questions. Don't see any on the Google thing. Could also run through a few of the exam questions quickly. Could be useful. On Piazza, I can post the answers to the questions there, obviously, as well. Doesn't look like there's any new questions there. So I can just jump through a few questions from, let's do last year's exam. Where is it? This is 2015. And I'll open the 2016 exam. Okay. Okay. Everybody see the exam? Probably. Anyway, so there's questions like, if sustainability is a combination of addressing today's problems and meeting future needs, how might you design something to address both? These are the type of conceptual questions that strive at seeing whether you have more than just the definition memorized, but also what we think about implementing the definition. Population growth, yeah, that's a similar question. So here's like a calculation question where, again, you can do the math in your head if you need to. So, and the part of the reason it may look like it because you have to do an exponential equation, you may think you need a calculator, but there's a reason on the exam sheet that I put down what E is, because if the growth rate were 2% and you have 50 years, then 50 times 0.02 is 1, so it's just e to the 1, so you wouldn't really need a calculator to do that, but you could still put it into a calculator to double check that that's the case. So, and then there's sort of thinking outside of the box questions like, if Italy's growth rate went from 0% in 2012 to nearly 2% this year, should they design a system to support the population predicted in B, which is 50 years of 2% growth? Probably not, because we understand that the growth rate is changing. And the main reason that which we talked about more, I think, last year, because there was a pretty also relevant this year politically, is the idea that how immigration affects population growth. And the reason that this wouldn't be possible for a global population is we haven't really figured out a way to move to Mars yet. So immigration is important for national statistics, understanding the rate of people moving in and out of countries. And so Italy's population growth is largely people moving in. And in terms of the planet, there's no way to have immigration because we're all stuck here. Okay. Generally, there's a few questions from precept processes. This question was getting at whether people understood what a section and a plan are in terms of thinking conceptually, which we had to draw also in the context of Jane's carousel, understanding a section is a slice, a vertical view of a concept, and then a plan is looking top down. And so there were a lot of people that didn't realize that a pyramid from the top was a square, which I was a little disappointed last year. But I'll try not to make it so dependent on people understanding what a pyramid was, because I didn't really want to test whether you knew what a pyramid was. So that was something we'll try and avoid, testing your knowledge of geometry of of structures. So population, yeah, understanding basic definitions again. Then there's some specific cases. We talked a lot about Singapore in class as well. So understanding some of these. And then anything where it says draw rough, don't worry about drawing super precise plots, just kind of a rough picture of what population growth will look like, sort of the demographic transition. And then, let's see. Again, a calculation question. Most of this can be done pretty much in your head. Again, here, this is an important step for estimating. If you do 1/420 is also almost 1/500. So again, it's good to have a calculator because you probably would want to do some of these on your calculator, but you could do it and you would not lose any credit for assuming that 1/420 is about the same as 1/500. So, and then again, of course, understand the difference between energy and power is an important concept to have for energy section. Adaptation and mitigation, we talked about. The social norm we didn't talk about because we didn't have Sander van der Linden give a lecture, but we did have some discussion more on policy challenges in terms of the discussion with Minister Mena from Chile, which there could be some overarching questions, not specific memorizing what he talked about, but what the takeaway messages were. Again, some concepts from how energy works, energy storage, and then again, what we just went over, impacts of nitrogen and phosphorus on the environment. Eutrophication is one of the big ones. Understand the difference between the reservoirs of nitrogen and phosphorus, right? Phosphorus is in the ground, we mine it, and nitrogen is largely in the atmosphere. It's the most common element in the atmosphere. Some energy questions about James carousel, and sort of then a understanding how you determine energy quantities from power, right? Power is the instantaneous, again, use. A light bulb is using 100 watts, an LED is using 10 watts. That's what it uses at one instant. In order to know how much energy it uses over a certain amount of time, you just multiply the power by time, and you can make these kind of unofficial units, like watt hours is a unit of energy. So a kilowatt hour is what you get on your electric bill. So if you multiply 1 watt by 1 hour, you get 1 watt hour. Or if you multiply 1 kilowatt by 1 hour, you get 1 kilowatt hour, which is a very straightforward way to convert a power unit into an amount of energy. So, right, there are some harder system questions generally that you have to really have a good grasp of the concept of energy balance. If you have the conversion rate of energy, it doesn't matter what form it takes. If it's all in the room, if it doesn't escape through the window, then the heat actually will all remain there, even though the light is being produced more efficiently by the LEDs. So it's kind of a tricky one, but it's more about understanding the first law of thermodynamics that we talked about. Energy into a system has to equal the energy out of the system. So if there's none of the energy from the lights is directly escaping the room, then all of that energy goes into the room technically and is eventually dissipated into heat. So I will check one more time for if anybody has any questions. Otherwise, I think this gets saved and I will send a link to it. So if not, if it doesn't get saved, then I hope it looks like one person is here, at least, maybe. Yeah, hopefully this was a good attempt to make up for not having a review session in class. And yeah, again, on the exam, best strategy is to do good assumptions, make assumptions if you're stuck, and round to the easiest number for you to do calculations so you don't get stuck doing extensive calculations. So, and again, yeah, synthesis of concepts, not memorization. Great. I will stop the broadcast then, and I'll look. Wait, I didn't look to see if anybody posted questions. One more time. I don't see anything. Okay, enjoy the snow day. I'm gonna go sledding with my kids now.